Okay, here we are, chapter 13. Chapter 13 is about fluids. So chapter 12 and 13 together here will constitute a unit, which we will have a test over at the conclusion of chapter 13. So chapter 12 was about matter, solids, liquids, and gases. We mostly talked about solids because this chapter, chapter 13, is about fluids, and fluids include both liquids and gases. Both of them have the properties of being able to flow and assuming the shape of their container. So both liquids and gases are fluids. There are some differences between liquids and gases, and we'll talk about those a little bit later. But many of the principles that govern fluids apply to both liquids and gases, and they are very important in the world in which we live and the way we go about life. So here we see a couple of examples, a drop of water in a container of water, creating the ripples and pouring a bucket of fluid of something into another container. And then even the sunlight shining through the water vapor and causing you to be able to kind of see the gas as the sunlight shines through it. Gases are challenging for us in many ways because we cannot see them. They're often transparent. So just a quick review of the idea of pressure, which we covered briefly last chapter. Pressure is force divided by area. Again, we talked about the whole principle of things that are sharp are going to have a lot of force over a small area, so they're going to have large pressure, so they're going to be able to cut through or to break things. And then we talked about the flip side of pressure, the idea of making the area very large, like in a snowshoe, so that your force divided by area is very low and you don't sink into the snow. What's important for us to understand about liquids is, unlike solids like rocks or boxes or something like that, which only exert their pressure downward, liquids will exert their forces also on the walls of the container. And even if they are in a sealed container, they will exert their pressure upwards, right? So this is just a picture, right, of a submarine. If a submarine was underwater, it wouldn't just be a problem if they had a hole in the bottom of the submarine, but also in the sides, because the water is going to squirt in the sides as well. So for liquids, we talk about the pressure a little differently, right? We could do force divided by area, but that's often less convenient because finding the total weight of the liquid is more difficult if the container is an unusual shape. So we can use kind of a shortcut for finding the pressure in a liquid. We can use the density of the liquid and how deep it is, right? Because the liquid is going to flow and it's going to stack up, but it's also going to flow. So all we need to know is how deep it is and how dense it is, and that will tell us what kind of pressure is going on at the bottom. We're going to have another number of videos again in this presentation. I have them highlighted in pink this time. You should go and watch them. They're again in the YouTube description if you're watching the video. They're in the notes section of the PowerPoint if you're just clicking through the PowerPoint. And what you need to appreciate is that this depth is very significant. So there's a little video of a tall container with holes in it, and it will show you clearly how the pressure changes with depth. And there's a little diagram there too, but the video's more impressive. So we've got pressure equals force over area. That was our old equation. And now we're actually going to end up with two equations that involve density and depth. And that's, again, as we talked in chapter 12, because there are two different ways of defining density, right? My preferred method is this second one, the mass density times gravity times depth. That's what most scientists would tell you is the formula for pressure in a fluid. But you can combine the mass density and the gravity terms together, right? Weight equals mass times gravity. So if you combine the mass density and the gravity together, that will give you weight density, and then there'll only be two terms of weight density and depth. But the density is critical and the depth is critical. The total amount is not critical. You could have a very tall, skinny column of water, and if it was 100 feet tall, you'd get the same pressure at the bottom of that tall, skinny column of water as you would 100 feet down in Lake Michigan. The total amount of water is not the critical part. So here's an example problem. What if we do have a column of water that's 20 meters tall? That's quite a tall column of water. Remember, there's approximately 3 meters to a story. So we're talking about a 7-story tall column of water. The weight density, of water is 9,800 newtons per cubic meter. Again, obviously the mass density of water is 1,000 kilograms per cubic meter, and we're just multiplying by the acceleration of gravity, 9.8, to get this 9,800 newtons per cubic meter. So we simply take the weight density and multiply it by the depth. We were given the weight density and the depth. We multiply those together and we'll get the pressure. Again, we discussed earlier the fact that a Pascal is a Newton per cubic meter, a very small unit. It's represented by a capital P lowercase a. My units are wrong here. The pressure is not 196,000 newtons, but 196,000 pascals. So one of the places where pressure is very important and where the whole idea of depth having a great influence is very obvious is when we talk about dams, right? So we dam rivers, we dam creeks to stop the water, and we want the dam to hold. We don't want to have some kind of accident or problem where the water we're trying to stop doesn't get stopped and actually goes through. So this first picture that I have is actually a dam in Egypt, damming the Nile River, and it shows a very significant image that captures a lot of the details of what it takes to build a good dam. There are 3 aspects to a good dam. The first aspect is that the dam needs to be thicker at the bottom. And this is perhaps intuitive if you watch that video. If we think about the fact that pressure increases with depth, the deeper in the lake we go, the greater the pressure is going to be, and therefore the stronger the dam is going to have to be to withstand that pressure. So the first rule is the dam needs to be thicker at the bottom. The second rule is that the dam needs to be thicker on the lake side. You don't just build a pyramid, you build an offset pyramid with more of the thickness underneath the lake. Now, unfortunately, I cannot show that in a real dam picture because the part of the dam that's under the lake is underwater, and so you can't see that part. So this picture is actually misleading in terms of the second point, because we see how thick the dam is sticking out here toward the downriver side away from the lake. But the reality is it's even thicker underneath the lake, underneath that water where you cannot see it. And part of this is because the dam not only has to keep the water from getting through it, it also needs to keep the water from getting underneath it. So if we make the dam thicker toward the lake, then the lake's weight itself is sitting on top of the dam, helping to hold it down and keep it from moving. And the third item is actually of the geometry of the dam itself, which again, you see this very clearly. The top of the dam where they have built a road here is arched toward the lake. The top of the arch is facing toward the lake. And this is, again, due to the strength concerns for the dam. An arch is a very strong shape if you are pushing down on top or on the crown of the arch. If you're pushing from inside the arch, not so much, right? A great example of this is eggs. Eggs are actually, even raw eggs, are hard for us to crush inwardly until there's a crack in the shell. But the baby chicks can break out of the egg even though they don't have opposable thumbs. So it's all about which side of the arch you are on. And if you're on the outside of the arch, above the crown of the arch, then it's very hard to break into the arch. If you envision a stone arch that has a keystone, Pennsylvania is called the Keystone State because it was the central state during the Revolution. But a keystone is this trapezoidal shaped stone at the top of the arch, and it really illustrates the power of the arch in one direction and not the other. So if we try to push down on top of the arch, we've got to make the fat part of the stone go into the small hole, and that's not going to work, right? Stone is strong in compression, it's not going to compress. That's not going to work very well. On the flip side, if we're pushing from inside the arch, we've got to make the small part of the stone fit in the big hole, and that, of course, is very easy. So the arch is strong in one direction and not the other. So we want to have an arched dam with the top of the arch facing toward the lake where all that pressure is going to come. more familiar dam perhaps in the United States. This is the Hoover Dam in Colorado, or between Colorado and Nevada, I think. Not Colorado, it's Colorado River. Arizona and Nevada, I believe, is where the Hoover Dam is. And again, it's a little harder, this aerial shot, to see the same aspects, which is why we have the other picture. But this is a very famous dam, damming the Colorado River, creating a very deep and tall lake, and then using that water for hydropower. When we build dams, we need to make sure that they do not fail. Some very famous failures have occurred in the United States. One of them is, it's called the Johnstown Flood. Again, there's a short little video in the description you can watch that will tell you the story of the Johnstown Flood. The upshot of that one was that if you get a lot of rain, then the lake behind your dam can fill up very fast. And if your dam is made of dirt, when the water starts coming over the top of the dirt, it's going to wash the dirt away and your dam is going to fail. I learned that lesson personally very vividly playing in the sandbox with the hose and sand when I was a kid. You could build tall sand walls and you could keep the water in for a long time, but when the water started going over the top of your sand wall, it washed the sand away and the whole wall failed very, very quickly. The other one that I want to talk about, the Johnstown Flood, was back in the 1800s, before we had many of our safety regulations in place. The St. Francis Dam was much more recent, in the 1950s, and it failed due to the fact that the two walls of the valley were made of different rock, and that was not understood when the dam was built. And so the one side was very strong rock, the other side was very weak, and the whole dam swung open like a door. And the lake that had been months, possibly years in the filling, all that water went down the valley all at once. Fortunately, it was a broader valley with fewer people living in it than the Johnstown situation, and so there were fewer fatalities. So how do we use water? We use water in many large number of ways in our lives. It's very important, even to our individual biological being, to be able to drink water. But physics-wise and construction-wise, we use water because water will seek its own level. It will level itself out. If you have a container and the water's deeper on one side than in the other, the water will flow until all the water is of the same depth. Maybe not relative to the bottom of the container, but relative to the center of the earth, right? If you tip a bucket sideways, the water still knows how what the ground is doing. The water still knows what level is, even if you tip the bucket. And that's because of pressure and because of gravity. And that's been understood for a long time. The Egyptians understood this. They used it to build the pyramids, as we're going to see in a moment in a couple of slides. It's just a little joke, right? The Egyptians 5,000 years ago built these pyramids, and 500 years ago during the Renaissance, they tried to build this tower, which now leans and is famous because it leans. Really, this tower's issue was not that they didn't know what level was when they built the tower. This tower had the same issue that St. Francis Dam had. The foundation was being built on two different types of rock, and as the building went up, the one type of rock stood firm and the other type of rock started to sink, and that caused the tower to lean. So here's just a visual demonstration of how the Egyptians used water to level things 5,000 years ago. They would dig down to the rock, and then they would dig these interlocking channels, almost would look like a lattice work or a grid across the rock, and then they would fill that lattice work with water. And since all of those channels were interlocked with one another, all that water would be at the same level. And then they would need to go around and mark that water level when the water was in the trenches. And that perhaps was challenging because you might have an evaporation issue where the final ones you marked would be lower than the first ones because the water would evaporate in the hot sun. But somehow they marked all that water level, and then they removed the water and cut the stone down to their marks and filled in all of the trenches, and then you would have a nearly perfectly level surface on which to build your structure. And we have found evidence that they did this underneath the pyramids, and in some of even their largest pyramids, if you go corner to corner across the diagonal, which is a vast distance, it's off by less than 1/4 of an inch from one corner to the opposite. And I've been in a number of much more modern buildings that are much smaller, and measuring from corner to corner of the room, it's off by way more than a quarter of an inch. So perhaps we should go back and learn from the Egyptians. But we did, right? Water seeks its own level. We do use that today. This little device is called the Pascal's vase, which helps to demonstrate this principle. They just have different shaped and sized tubes. And if you watch this little video, again, in the video description, they will show you filling up one of those tubes. And there's a tube here at the bottom that connects all of the tubes. So when they pour some more colored water in the big tube, that colored water is deeper here, so there's greater pressure at the bottom, right? Density times depth, greater pressure at the bottom. And so that greater pressure is going to push the water in the other tubes up, and the water is going to flow over and fill those tubes until they are at the same depth as the original one, right? As the original one gives it water, its depth is going to decrease and the other depths are going to increase. And when their depths are all the same, the pressure at the bottom will be the same, equal pressure will be balanced, and the water will stop flowing. And this happens very quickly, but it's how water seeks its own level. Because it can flow and because gravity pulls it downward, it's always going to maintain a levelness relative to the center of the earth across any fluid body that is connected, right? So that it can flow from one to another. Now, you can get situations like Death Valley, right? Where you have a space that's below sea level that's not full of water. But the problem, the reason for that is there's no connection between the ocean and Death Valley, so there's no way for the water to flow through, right? There's a mountain range, there's rocks in the way that prevent the water from flowing to that lower location. Again, the Egyptians did this, and we do this today with construction, right? We don't dig channels in the rock, but we have this device, we call it a level. Because we're very practical people, and the goal of a level is to make things level. And inside that level, we have little glass tubes, and in those glass tubes, there's mostly a liquid, but then there's a little bubble of gas. And so as we place the level on a horizontal surface, the glass tube is just slightly curved, so that slightly curved in that way, so that if the surface that we're sitting on is perfectly horizontal, the bubble will end up in that the highest part of that curve. And they've usually put little lines on the glass so that all you have to do as a construction worker or as the person using the level, you don't have to understand all the physics. You just know you want that bubble between the two lines, and that means that that my level is now horizontal, which I did not draw it horizontal at all, but that is what that indicates. And then we just turn the glass tube 90 degrees so that we can check whether the surface is vertically straight. And then sometimes you get tubes that are at 45 degrees as well. Often these tubes are not actually filled with water. Water has too high of a freezing point. You wouldn't want to leave your level outside accidentally and have it freeze. So you put some other liquid in there that has a lower freezing temperature, whether that's alcohol or kerosene or something of that nature. So water seeks its own level, and we make great use of this in a municipal manner in the way that we are able to have water pressure in our houses. Right? They build a water tower and they pump water up into that water tower, and then the water tower is connected to our houses, to our schools, to our fire stations by pipes. And there is actually no pump in that water system. There's a pump to get it up to the water tower, but then there are no further pumps. It's not necessary, right? You have some water that is up here that is at a great depth or a great height, right? The same thing, right? This is a vertical distance. If it's going down below you, we tend to call it depth. If it's going up above you, we call it height. But the point is, the water is some great distance above where the water is being used, and as a result, there's going to be great pressure down there. So that's why our water towers have to be towers. That's why we have to put them up in the air, because it is that physical height that generates the water pressure that allows the water to squirt out of your shower and give you good water pressure, and gives the firemen good water pressure when they're trying to put out fires. Now, they have pumper trucks. They increase the pressure as well when they're fighting a fire, but that's why we have water pressure in our water system. Now, if you live out in the country and you don't have access to city water that's connected to a water tower, then you do have a pump that's necessary to create the pressure. And the pump usually fills up a tank at a certain pressure, and then you can use the water. And the problem with that, of course, is that if you lose electricity and your pump can't run, then you lose access to your water. In the city, that does not happen because those water towers are large, half a million gallons, and they have backup generators that can run those pumps to maintain water supply to the population. So we also we have pressure is force divided by area. So we can undo that, right? Pressure is force divided by area. So if we want to go from pressure back to area, or from pressure back to force, all we have to do is multiply by area. So pressure times area will equal force. So that's what we have done here. We have pressure equals weight density times height. And now we take weight density times height and we multiply it by the area as well. And that will tell us what the force is going to be on the bottom of the water tower. But remember, fluids do not only exert pressure downwards, they also exert pressure on the sides. So if we want to calculate the force on the side of the water tower, it's a matter of how far down we are, right? So if we are halfway down, we will use the calculation for the lateral area, and then they're calculating the total force on the walls of the water tower, which is the lateral area, the area all the way around, and then we take the average half of the height to calculate that total force on the side. So another effect that we have with fluids, and this one in particular is very important for liquids. It is true for gases as well, but due to the fact that gases are compressible, this does not translate in quite the same way for gases as it does for liquids. So Pascal's principle says that any change in the pressure on an enclosed fluid is transmitted to all other points in the fluid and acts in all directions. So sometimes we get a little confused, right? We've been talking about density times depth determining the pressure. And now we have this Pascal's principle that says that the change in pressure is going to be the same everywhere. So it's a little confusing to people sometimes. The key that we need to understand is that this is about the change in the pressure, not the pressure itself, right? So if we just had this tube of water here in this picture and we didn't do anything to it, yes, the pressure at the bottom of the tube would be greater, the pressure at the top of the tube would be less. Because the difference in their depths. But what we're talking about with Pascal's principle is when I whack the tube with the hammer, that's going to squeeze that stopper into the water, and it's going to increase the pressure. So it is this change in the pressure that we are talking about with Pascal's principle. This change in the pressure is transmitted to all other points. It pushes outward on the glass. It also pushes outward on the other rubber stopper. It's this fun little device that physics teachers like to buy. It's basically a round glass tube with a plunger, and this glass sphere has tiny holes on all sides of it. And so you fill this thing up with water, and you shove the plunger in, and the water squirts out all different directions with the same pressure, and you get all your students wet. But it shows that the pressure in all directions is the same due to the change in pressure is the same, right? Because I push the plunger in, this is causing a change in pressure, and that change is the same on all the glass walls of the tube. So our change in pressure that we introduce somewhere is the same pressure at all other points. And you can see there are some equal signs that we're going to use to be able to solve these problems. So this is the whole principle behind hydraulics, right? This is how we go ahead and we use this principle to be able to lift things with less force, right? It's very similar to what we did with simple machines, right? Force and distance, right? We could put in a small force for a large distance. For example, pulling a rope on a pulley system, you pull a lot of yards of the rope and you don't lift the object very much, but the object gets lifted with a much greater force than you are exerting on the rope. So it's that same principle, and it's the same, we're not cheating. There's that same distance versus force trade-off here. So you get a hydraulic system with pistons and some kind of liquid inside. Now, again, I said it works better with liquids than gases. The problem with gases is that gases compress. So you shove this piston down. If this was all just full of gas, the gas would compress and the pressure in the gas would go up, but not by very much because gases are compressible. Liquids are not compressible. So when you shove down on this piston, the liquid has to go somewhere, and it goes up over here and shoves this piston upwards. So we have two different size pistons, right? So this is a little piston. We're going to put a little force on it, kind of like the lever analogy. We're going to put a little force on the long arm. Here we're going to put a little force on the small piston, and that's going to produce a much bigger force, because whatever pressure, remember, a pressure is a per area thing. So we're going to create some pressure here, and that pressure is going to be spread out over a much bigger area and therefore deliver a bigger force on the other side. But of course, here we have a small cylinder. So if we push it down a centimeter, this cylinder is not going to go up a centimeter, right? We're not going to have enough liquid to cause this cylinder to fill up by a depth of a centimeter. So it's that same trade-off. We're going to have to push a lot further here, and then this one's going to go up. And that's what we have with hydraulic lifts of all kinds, right? This is a little hand-powered 2-ton jack, and you can see the size of the cylinder over there versus the size of the cylinder over here. And then you put a stick in that hole, and you get the added mechanical advantage of a lever plus the mechanical advantage of a hydraulics that are using Pascal's principles. So you get those two things put together, and then you get a person pushing down, creating 4,000 pounds worth of force, right? That's what 2 tons is. So here's one with actual numbers that we're going to go ahead and do. Again, this is how your mechanic lifts your car up in the air so he can work and do an oil change or change the tires. It's all based on hydraulics. Now, in theory, we could build a water hydraulic system, and they do have some water hydraulic systems, but they tend not to do water hydraulic systems because water is extremely corrosive to metal, and we tend to build these systems out of metal. And so if you have a liquid in there that's going to corrode the container, that's going to shorten the lifespan of your object. Plus, water is fairly prone to evaporation. So they like to use oils instead because the oils play nicer with the metal parts. Plus, they often have a self-lubricating aspect to them, and they're much less likely to evaporate if you use the right oil. Right? If you use the wrong part of petroleum, then it is more prone to evaporation. But so here we have a little piston that has a cross-sectional area of 3 square inches, and we're going to put 15 pounds on it. And it's connected by a tube, by an enclosed tube, right? That's important, the enclosedness of it. I used to read Hardy Boys stories when I was a kid, and they would always be getting close on the mystery, and then somebody would sabotage their car, and they'd sabotage their car by cutting the brake line. So the brakes on cars are hydraulic systems. When we talk about standing on the brakes, there was a time when you had to stand on the brakes because it was literally your weight against the wheels that was stopping the car. And that was all the more you had was your weight. And so vehicles were limited in their size because, the driver had to be heavy enough to stop the vehicle. And if the truck gets too big and is carrying too much weight, even a very large truck driver would not be able to stop it in time. So we have moved on to hydraulic brakes, where when you push on the brake pedal, it's like you're pushing on this little cylinder, and then that liquid is pushing against the brake disc or the brake cylinder and causing your car to stop, and therefore you don't have to deliver the same force that you need, but it has to be enclosed. So those Hardy Boy books, the guy would go in and he'd slit the brake line. Well, then you pushed on the brake pedal and the liquid would all squirt out the hole because we no longer have an enclosed fluid. If you don't have an enclosed fluid, Pascal's principle fails, the liquid just escapes, the pressure doesn't go up, and your brakes fail, and then the bad guy was hoping they'd run a red light and get T-boned, and no one would ever notice that he'd cut the brake line. But the Hardy Boys always managed to escape. They destroyed large numbers of vehicles in the process, but they always managed to escape. So I'm getting off topic. Back to this problem. So we got 15 pounds, 3 square inches, unknown force, 75 square inches. So we just plug these in there, right? I left the pressures in, but the pressure really doesn't need to be in there, right? Because they're the same. So we could just say 15 over 3 equals F2 over 75. It's a simple ratio. You cross multiply, you divide, or you can, 15 divided by 3 gives you your 5. 5 times your 75 gives you 375 pounds. So our 15 pounds became 375 pounds. We basically have a mechanical advantage there of a factor of 25. So our force was increased by 25 times. Now, the flip of that, of course, is that we're going to have to push this piston 25 times further than this piston's going to go up. So again, no such thing as a free lunch. We're not creating energy. We're not creating work. We're just changing the way the work is expressed to a form that's easier for us to do. So pressure is extremely important in liquids and in gases. We're going to talk now more about gases, well, both gases and liquids. Again, it is very hard for us to envision what is going on with a gas, particularly the gas in the atmosphere, because that gas is invisible and we tend to forget that invisible things exist. So there's a whole bunch of things that we do in life in which gases are actually exerting pressure, and we don't realize that, and so we describe things in a misleading way. So the first one, of course, is drinking from a straw. We've all drunk from straws before, and we all know how you do it. You put your mouth on the straw, you seal the straw off with your lips, and then you take the air that was in your mouth and you drop your diaphragm and you store that air in your mouth in your lungs, and that causes the pressure in your mouth to drop, which causes the pressure in the straw above your liquid to drop. So now we get low pressure in your mouth, low pressure at the top of the straw. Well, we don't have low pressure outside of the straw, right? We still have normal atmosphere pushing down on the surface of the glass. So the atmosphere pushes down on the surface of the glass, and the pressure inside the straw is less than normal pressure, right? Before you put your mouth on the straw was full of the same air that was outside, right? The same air, the same density of air, 14.7 pounds per square inch at atmospheric pressure. You had 14 pounds on every square inch in the glass. You had 14 pounds on every square inch inside the straw. You had equal pressures, and so they were balanced, right? Think back to that Pascal's vase with that green water in it. Everything was the same level. So if you put the straw in the glass without your mouth on it, you're going to have liquid in the straw at the same level as the liquid in the glass. But when you lower the pressure in the straw, you have more pressure outside, less pressure inside, and the atmosphere pushes the liquid up the straw. Now notice the key there is push. The atmosphere pushes. Nothing pulls the liquid up the straw. Doesn't happen, okay? That's what people think, right? When they use that word, it starts with S, ends with uck. They use that word, they think that they are somehow pulling liquid up the straw. Isn't happening. The atmosphere is pushing the liquid up the straw because you created a lower pressure region in your mouth. If you don't have a seal, you won't be able to lower the pressure, right? Again, when I was young, I had immature cousins, and we would go to a restaurant together, and they would take great joy when somebody went to the bathroom. They'd pull up the straw, and they'd take a knife, and they'd make a little slit in the straw, and then they put the straw back in their drink. And the person would come back and they'd take a sip and everything would be fine. But when the liquid in the glass got below that cut, suddenly their straw wouldn't work and they'd get this funny look on their face and everybody would laugh at them. But that's because the pressure, the gas was no longer sealed, right? So now they're trying to create low pressure in their mouth, and instead of the liquid getting pushed up the straw, the air just takes a shortcut in the cut in the straw and comes into their mouth, and then you don't seal off and lower pressure, and so the atmosphere can't do its job. So that's drinking from a straw. Vacuum cleaner, same principle going on here. We call it a vacuum cleaner because there is a vacuum pump inside of the vacuum cleaner. A vacuum pump is simply something that pumps air. That's all that it does. It is pumping the air. So we have a vacuum pump and it's taking the air that's inside the vacuum chamber and it's pumping it out, right? when you run your vacuum, you can stick your hand somewhere on that vacuum and feel air blowing out. That's what the vacuum cleaner does. It takes the air and removes it. And when it removes the air, then that chamber inside has less air in it, less air, less pressure. The pressure is lower, and the fluid outside is going to try to rush in to equalize the pressure. Again, think of that green liquid in the Pascal's vase. The pressure is trying to balance, is trying to equalize. Here in the glass, it was trying to equalize, and we could see the liquid moving. Here you can't see any liquid moving because it's all just gas. Gas is trying to rush in and equalize the pressure. And of course, it never succeeds because now we pump more gas out. But in the process, the air is rushing in this hose, and it brings the dust and the dirt in with it, and that's how we, quote, vacuum stuff up. You got to have a good vacuum cleaner so that you don't have the dust get drawn right out the fan and blown right back into the room, right? That can happen with a poor filter, or sometimes you get a clogged filter and then you don't have very much pull at all because the vacuum pump can't pull very much air through a clogged filter, and so you don't get a very big pressure difference and you don't get very good S followed by UCK, right? That's what we say a vacuum cleaner does, but in reality, it's the atmosphere pushing the gas inside. We have various other strategies today. We don't have a lot of vacuums that look like this anymore. Various other strategies to keep from just recycling the dust back into our house. One strategy is the whole house vacuum, where this actual vacuum portion is fixed to a wall somewhere, and then the hose is essentially really long, right? You plug the hose into different outlets around the house, and then it goes in that way. And usually a whole house vacuum, the vacuum portion is mounted in the basement or in the garage. Either case, it exhausts outside. So if your filter fails, and if the dust is getting out and not being captured in there, at least it's being thrown outside and not back into your house. And the other strategy is the rotary vacuum, like the Dyson vacuums, where they actually spin the air in a circle. And as we learned in chapter 9, circular motion, centripetal force, when you spin something in a circle, the more massive stuff, due to its mass, will go to the outside. So the Dyson vacuum, they spin the air in a circle, and then they remove the air from the center, and all the heavy dust and dirt particles end up around the outside of that chamber and doesn't get pulled out and dumped back into the house because the air itself is lighter than any of the dust or the dirt. So both of those using physics basically to solve this problem. But the vacuum cleaner does not S followed by UCK either. It is a pressure difference that we are creating with a vacuum pump so that the atmosphere will push gas into the vacuum cleaner, just like the atmosphere pushes liquid up the straw. And finally, we have that device that is actually named after S followed by UCK, the suction cup, which again, people think, oh, I put a suction cup on something and it pulls, right? It pulls the object and causes it to somehow to follow after the suction cup because it pulls somehow magically. No, again, it's simply the atmosphere. Suction cups are usually rubber, some flexible material like rubber, and you take the suction cup and there's usually an opening underneath that is initially full of the same air as the outside. So if you just set a suction cup on a table and then pick it up, there's no suction, it just comes right back off. But when you put the suction cup down and you push it down initially, what happens is the gas inside slips out the edges, right? Just like you can think of squeezing a balloon that's not closed. You're going to squeeze the gas out, okay? But then when you let the suction cup up, these edges seal and the gas can't get back inside. So what we have done is removed some of the gas from this space and then recreated the space. Well, now the gas that's left in there has to spread out. When it spreads out, there's less of it to push against the walls, there's less pressure, there's the normal 14.7 pounds per square inch on the outside pushing down, and so now we have more pressure pushing down, less pressure pushing up, and so we end up with a net force downward, holding the suction cup to whatever surface is there. And again, this is force. This is the atmosphere pushing. This is not something pulling at all. And it can add up very, very quickly. I have a suction cup at the high school that's 10 inches by 10 inches. So 10 inches by 10 inches, that's 100 square inches. Again, atmospheric pressure is 14.7 pounds per square inch. If I put that suction cup on something and squeeze, say, half the air out, now we're talking about 14.7 on the outside, only 7 something on the inside. We're talking about a difference of 7 pounds per each square inch on that suction cup. Well, it's 100 square inches, and that's not even a very big suction cup, right? I mean, typical computer screen's more than 100 square inches. You're talking about 700 pounds of force holding the suction cup to the surface because of air pressure differences. So the atmosphere can be extremely powerful if we can harness it in that way. We don't usually notice the power of the atmosphere because the pressure is almost always equal. Again, we say nature abhors a vacuum. Really, it's about the fluid trying to flow and equalize pressure. And so naturally, those pressure differences don't occur very often. And so we miss the power of the atmosphere because we don't see it very often and because the gas itself is invisible. And so we make up a word, S followed by uck, to say that we pull on things, somehow pull on liquids. When you think about a liquid or a fluid and how it flows, the idea of pulling, I mean, stick your hand in water sometime and try to pull the water out. It doesn't work. It can't be done. It just flows away from your hand. But what is really going on here is a push. It's always a push. So hopefully this message has come across clearly to you by now. Nature doesn't, and of course physics doesn't either. So another thing that we use with all of this pressure is something called a barometer. A barometer is a device that we use to measure the pressure in the atmosphere. And this has several practical uses, right? So one of those uses is simply to measure the pressure. So weatherwomen, they use barometers all the time because small changes in pressure are indications of how the weather is going to change in the future. So weather people have barometers to measure the pressure. In fact, for hundreds of years, sailors have had barometers as well, right? They didn't used to have access to satellite radio or the internet to know what weather was going to do, but they could take a barometer on their ship and they could watch how the barometer responded, and that would give them warning when a storm was going to come. And particularly back when they had sailing ships, it was extremely important to know before the storm arrived that it was coming, because that changed how you put out your sails and your ropes and all of that good stuff. So barometers measure pressure. I used to think when I was a kid and I watched the weather, they had these H's, these red H's, always on the map, and I always thought that the red H stood for hot. But after a while, I realized, wait a second, the other letter on there isn't a blue C for cold. There are red H's and there are blue L's, and the H and the L stand for high pressure and low pressure, and that those changes in pressures, again, ultimately determine the occurrence of precipitation and that sort of thing. But one of the other applications of the pressure changes is the idea of elevation, right? We understand the idea of an ocean, and we understand that as you go deeper in the ocean, density times depth, as you go deeper and deeper, the pressure of the water is going to get greater and greater. What we don't appreciate all the time is the fact that the Earth that we are living on and this atmosphere that we are breathing is an ocean as well. It's a little bit different ocean. It's 100 kilometers deep, but it is still an ocean. And again, the atmosphere is a little different because it's not the same density all the way down, much greater compressibility of gas than of liquid, but still there's pressure. And as you go up in the atmosphere, the pressure goes down, right? It's 14.7 pounds per square inch at sea level. Well, sea level, roughly 70% of the planet is at sea level, right? The oceans cover 70% of the planet. But as you go up a mountain and you get higher and higher, the pressure that you experience becomes less and less. And that can be very effective in measuring your elevation. So actually, mountain climbers, right? Do you ever wonder how they know how tall the different mountains are? You ever wonder how they can compare mountains on different continents, right? You can't get a big tape measure and measure all the way from the ocean. That's not going to work. But you can climb that mountain with a barometer, and you can measure what the pressure at the top of that mountain is. And because the whole world is a single ocean of air, you can compare K2 in Africa to Mount Everest in Asia to Denali up in Alaska, and you can compare their heights even though they're at different parts of the world. And of course, also airplanes use this. They use this extensively for determining the height of the aircraft. In fact, the altimeter, the thing that tells you the height of the aircraft, is directly connected to a pressure sensor. That is how they tell you your altitude. I used to wonder why it was that airplanes would always have their altitude or report their altitude in feet above sea level. Even if you were flying from, say, St. Louis to Kansas City, they talk about what your altitude was in a distance above sea level. And I was like, well, that's dumb. How high are we above the ground, right? You don't fly over the ocean going from St. Louis to Kansas City. But it's because their instrument is based on pressure, and that pressure is based on sea level pressure. And so it's not enough to fly and to know what height you're at. You also have to know what height the ground is at, right? Doesn't do you any good to be 2,000 feet above sea level if you're flying into Denver, because Denver itself, right, the Mile High City is 5,000 feet above sea level. So that would not be so good if you were 2,000 feet above and the ground was 5,000 feet above. That would mean that you were going to crash. Anyway, so the barometer works similar to the straw situation, right? We've got air pushing down on a container of liquid, and then that liquid is connected to be able to go up into this glass tube. Now, the big difference between a barometer and a straw is that the barometer is closed at the top. It looks like an upside down test tube, although it's much taller than a test tube. It's closed at the top, and there is nothing in there, right? That's a vacuum. The vacuum, we talk about the vacuum of space. A vacuum is the absence of anything, not just the absence of solids or liquids, but also the absence of gases. There is nothing up there. Because there is nothing up there, there is nothing pushing down on that liquid with any pressure, right? When you drink from the straw, there's still some gas in the straw, some gas in your mouth that is pushing down on the liquid. There is nothing in there pushing down on the liquid. So there is only the pressure here at the bottom of the glass tube. There's the pressure from the weight of the liquid, but there's no pressure from gas above the liquid because there is no gas above the liquid. So we just have the liquid column pressure, and we have the atmosphere column pressure. Now the atmosphere goes up 100 kilometers, right? And the liquid only goes up here a number of excuse me, inches or centimeters, okay? But the liquid is much denser than the gas. So if the atmospheric pressure goes up, if the atmospheric pressure gets higher because of a new weather system moving in, there will be more pressure pushing on this container of mercury, and more mercury will get pushed into the tube. And therefore the reading here will move up, and we'll say, oh, the mercury is rising, the barometer is going up. That means that a high pressure weather system is coming in. And when the reverse happens, when the atmospheric pressure goes down, then there's less pressure on this mercury, and there was more mercury in the tube, so the mercury pressure is greater, and so the mercury is going to flow out until the column gets short enough that its pressure is the same as the air pressure, and then it will stop falling. And so we look at the glass and we say, oh, the mercury was falling. So sometimes you read about that, in books, or especially in these sailing books, they'll talk about the glass and whether the mercury is rising or falling, and what that's going to mean in terms of weather. Now, we do have two different types of barometers. A big glass tube with a dish of mercury would be kind of inconvenient to take on an airplane, especially if you're one of those pilots who likes to, turn your airplane on its side or roll it over or something like that. They make a real mess of your mercury. So we have a second type. It's called an aneroid barometer. It uses pressure differences between the inside and the outside. So this is a sealed container. When the outside pressure goes up, it will crush this accordion-shaped thing, and it will tell us, higher pressure. And when the outside pressure goes down, then this accordion container will expand until the pressure inside and outside are equal again, and that will cause this little lever to go down, and it will say, you're at lower pressure. So that's how it works. Then you don't need any mercury. Again, we use mercury for a very good reason. If you recall, at the end of chapter 12, we took a look at the density of some different materials, solids, liquids, and gases. Most liquids had a density of around 1,000 kilograms per cubic meter. Water is exactly 1,000. Seawater is a little more, oil's a little less, but mercury was 13 times denser than water because mercury is actually a metal. So, but it's a liquid. It's a very dense liquid. So we like to use mercury barometers, even though mercury is toxic and would be dangerous to consume in any form. But because it is so much denser, we are allowed to make a column that is so much shorter, right? Pressure is density times depth. So if we're 13 times denser, we can be 13 times shorter and have the same pressure. A water barometer would be very inconvenient, right? We did that problem earlier on where we talked about a 20-meter column of water and we got a pressure of 196,000 pascals. Well, atmospheric pressure, I've been talking about 14.7 pounds per square inch. It's 101,000 pascals. So a column of about 10 meters, or again, roughly 3 stories, a little over 3 stories worth of height. That's how tall the water would need to be to create a pressure equal to what the atmosphere makes. Now, again, 3 stories sounds tall, but you got to remember the atmosphere is 100 kilometers tall. So it's very, very tall, but gas is much less dense than liquid. But walking around with a 3-story tall glass tube would be very, very inconvenient. So nobody has water barometers. There are some science museums that have a water barometer just to make this point, right? But instead, we use mercury barometers. Mercury barometers then can be less than a meter tall. Atmospheric pressure is 76 centimeters of mercury. Actually, usually we say it in millimeters because the changes are small. So we say 760 millimeters of mercury is atmospheric pressure at sea level. And then, of course, you need one a little bit taller than that so that the pressure can vary up or down from there. So now we're going to move on to this idea of buoyancy. What makes things float or not float? And this, again, applies to both liquids and gases, but we're going to talk primarily about liquid examples. But please remember, right, hot air balloons, blimps, there are certainly situations where things float in a gas as well. We're just not going to be using that example quite as much. Before we can go into the idea of buoyancy, we have to get another idea established, which again, we talked about in chapter 12. When we talked about density and how do you find the volume of something, so you can do mass divided by volume to get density. And that's this principle called the principle of displacement. And this says that when you put something in a liquid or in any fluid, really, it's going to have to push other parts of the fluid out of the way, right? So we got this little picture here that shows it very clearly, right? We've got an irregularly shaped rock and we've got a graduated cylinder. The graduated cylinder reads 150 centimeters when there's nothing in it, 150 milliliters, sorry. We put the rock in and that makes the water get deeper. Again, if you've ever stepped in a bathtub, you're familiar with this principle. If you've ever jumped into a ball pit at McDonald's, you're familiar with this principle. When something goes in, something else has to move out of the way. 2 objects can't occupy the same space at the same time. So there is going to be a displacement of liquid when you put something else inside, okay? So this is a way to measure the volume of the rock, right? We put the rock in, we see that it's now reading 180 instead of 150. So we know that we subtract those and the rock has a volume of 30 milliliters, even though it's an irregularly shaped rock. So we need to understand this idea of displacement before the idea of why things float are going to make sense. So the principle of buoyancy is expressed in what we call Archimedes' principle. He was a Greek scientist who lived about the time the Romans were replacing the Greeks as the world power. He actually lived in Syracuse, but he expressed Archimedes' principle as an immersed object is buoyed up by a force equal to the weight of the fluid it displaces. So if you put an object in a fluid, it's going to push some of the fluid out of the way. And it's going to get pushed upward because it's pushed some of the liquid out of the way. And it's going to get pushed upward by a force, we call it the buoyancy force, that is equal to how much weight of fluid it is pushed out of the way. Okay, so here's a little pictorial example that will help perhaps this make some sense. So we've got an iron cube here hanging on a scale, hanging in the air. Okay, so this scale reads 3 newtons. So this piece weighs 3 newtons, and we have it above a container of water, completely full of water. And next to this container, next to the spout, we have an empty container that we've hung on a scale, and we've reset the scale to read 0 with the container on there. Okay, so now we lower the object into the water. Whenever you lower an object into the water, it seems to weigh less. It appears to weigh less. We call this apparent weight. This object went from having a real weight of 3 newtons to an apparent weight of 1 newton. It appears to weigh less in the water. If you've ever tried to lift something out of the water, this becomes immediately apparent, right? Maybe you could pick it up off the bottom of the pool and you can get it up to the surface, but when you try to get it out of the surface, it somehow seems to weigh more. That is what is going on here, because when we lower you into the water, there's now a buoyancy force pushing up on you from the water. And in this case, then the scale doesn't have to pull up as much because the buoyancy force is pushing up with some of the force, okay? And so as we lowered it in, we caused the water to overflow. Displacement, right? The principle of displacement. Well, how much water overflowed? Well, this is why we have this second scale sitting here. When we lowered it in, some water overflowed, and exactly 2 newtons worth of water flowed out of that beaker and into this pan. So we spilled out 2 newtons worth of water. We displaced 2 newtons weight of water, and lo and behold, our weight of 3 newtons has suddenly magically been reduced. 3 has come down to 1. We've been reduced by 2 newtons. We're being held up by a buoyancy force from the water of 2 newtons. Now we know iron is denser than water, and if we did not have this scale here, the thing would fall all the way to the bottom. It would still sink because it weighed more than the buoyancy force, because 3 is still more than 2, and the object would sink all the way to the bottom. But what if we had something else, something that only weighed 1 to begin with? As we lower it into the water, the buoyancy force is going to increase as it displaces water, and the buoyancy force is going to stop increasing as soon as they are equal, right? If we lower it in and we displace 1 newton worth of water, then 1 newton worth of we displace 1 newton of water, we'll have a buoyancy force of 1 newton, we'll have a weight force of 1 newton, and the object will stop sinking into the container. So then it will only be half in the water and half out of the water. It won't keep sinking once those forces are balanced. Now we can force it under, right? If you've ever shoved a beach ball underneath the surface of the water, you force it underneath, and now the buoyancy force is bigger than the weight force, and when you let go, it's going to shoot that beach ball out of the water. So we are buoyed up by a force equal to the weight of the fluid it displaces. There's 2 ways to think about this. One way of thinking about it is from a pressure perspective, right? The deeper we are, the greater the pressure. So the bottom of this cube is deeper, and therefore the pressure on the bottom is going to be big, and the pressure on the top is going to be less. So more pressure on the bottom, less pressure on the top, that's going to create an upward push, okay? And how much upward push? Well, remember, pressure is force divided by area. So if we want to figure out the force, we got to take the pressure and multiply it by the area. So what's the pressure difference? Well, that depends on the height. And how big is the area? Well, that depends on the cross section. So if you take the height, you multiply by the cross section, that comes out to be the volume. The volume times the density difference, or times the density of the water. The volume times the density of the water is the weight of the water displaced. So you can think of it in terms of pressure. You can also think of it in terms of As a former physics teacher colleague of mine says, water is stupid. Water is stupid. Water doesn't know that you put something in the water. Before you put something in the water, that chunk of water weighed 2 newtons. You stick something in the water, water's stupid. It doesn't know any better. It still holds the object up as if there's 2 newtons of water there. So it pushes up with a force of 2 newtons, because that's how much it took to hold up the water. So Archimedes' principle can be kind of a challenging idea. There's a lot of different pieces you have to put together. The density part, the volume part, the weight, the forces part. So this is important. Got another little 5-minute video from Eureka. They do a really good job of trying to drive home this idea, this principle, using numbers and using a metal example, a plastic example, a cork example. So pause my video, go watch that video, and then come back and continue. So really, we talk about the fact that things have a buoyancy force. That's an upward force. And everything that gets put in a fluid of any kind has an upward force. You and I have an upward buoyancy force on us right now because we're sitting at the bottom of an ocean of gas, the atmosphere. Now, to tell you the truth, it's not a very big force, right? Our volume isn't huge, and air's density is very, very low, and so the buoyancy force on us is very tiny. But there is a buoyancy force. Whether you sink or whether you float or whether you do anything, there's always a buoyancy force, okay? But we talk about things floating, right? We tend to notice the buoyancy force more when an object actually floats because we say, hey, what's holding that thing up? So ultimately, it comes down to a comparison, right? A comparison between your weight force and your buoyancy force. And if we think about this a little bit, our weight force, as we learned way back in chapter 5, weight is mass times gravity. But we have just learned that our buoyancy force is equal to the weight of the fluid we displace. Well, we displace a fluid that's equal to our own volume. So we take the volume of the object and we multiply it by the density of the liquid. Okay, so we've got our weight, which depends on our mass, and we have our buoyancy force, which depends ultimately on our volume. So we really come down to comparing our mass and our volume, right? Do we have more mass or more volume? Well, compared to what, right? Well, if we take mass and we divide it by volume, then we get something that we call density, right? Density. And so we got to compare our density to the density of the liquid. So if we are denser than the liquid, we're going to sink. If we are less dense than the liquid, we're going to float, right? If we have more mass per volume than the liquid, we're going to sink. If we have less mass per volume than the liquid, we're going to float. Okay, if we have exactly the same, we're going to do this funky thing where we're suspended, which means we're at whatever level we're at. We don't rise in the liquid, we don't sink in the liquid, we're perfectly the same density as the liquid. That's a pretty rare phenomenon for non-living objects. We'll talk about other objects later. But when your buoyancy force is greater than your weight force, you are going to rise to the surface and you are not going to remain fully submerged. You're going to rise until it, maybe a tenth of you's out of the water, maybe 90% of you's out of the water, maybe half of you's out of the water. All of that depends on your density's size compared to the density of the liquid. Because again, you're going to hit equilibrium. Nature loves equilibrium, right? So if your weight force was bigger, you would be sinking. If your buoyancy force was bigger, you would be floating. When those two are exactly equal, then when your buoyancy force is greater, you'll be rising. See, this is part of where we have confusion because we use the word float to mean something rising toward the surface, and we also use the word float to mean something staying still on the surface, and that is confusing, admittedly, okay? But when something floats on the surface, the buoyancy force and the weight force are equal. They have to be, otherwise you wouldn't be sitting still on the surface like that. So this is a really important idea, and there's going to be a number of math problems that we're going to do this chapter. They're going to revolve around this idea of buoyancy and floating, okay? And so I have listed not one actually, but 3 different videos explaining in detail how to do these buoyancy problems. They just, easier for them to do the drawing than it is for me to do all the drawing on PowerPoint, and sometimes the pictures are really important for these. So I actually posted 3 different YouTube videos of 3 different people explaining how to do a mathematical buoyancy problem. I would strongly recommend that you watch all 3 of them, and then as you're trying to do the homework, you come back and you watch them again as you get stuck. It will be very helpful for you. So I'm going to talk here about 6 examples here quickly, trying to drive home this idea of Archimedes' principle and how it works and how it doesn't work, with some real life examples that hopefully you can relate to. The first one is submarines, which we're familiar with, these boats that can float on the surface or they can go underneath the surface, control their depth. They can go all the way to the bottom if they would choose. And the way a submarine operates is by, again, playing this game between its mass and its volume and adjusting its density. And it does that by an exchange of gas, which has a very low density, and water, which has a much higher density. So the submarine actually has 2 hulls, two parts that keep the water out, an outer hull and an inner hull, and the people stay inside the inner hull, but that space between the hulls can be filled either with air, as is the case here when the ship is wanting to be at the surface, or they can fill it with varying degrees of water to adjust their density and cause them to sink to a greater or lesser degree. So that's how a submarine controls its depth, by an exchange of gas and liquid to change its density. Life jackets, how does a life jacket help you float? We know that the human body does float, right? You took swimming lessons and they taught you to float on your back. But the problem with the fact that human bodies float is that we don't float very well. I guess that's the wrong word. It's not that we don't float well, it's that most of our body has to be below the surface to displace enough liquid for us to float. And that can be a problem if we're trying to, not take any liquid in our nose or mouth when we breathe. So a life jacket helps us to float better, but it does not make us lighter. That's a common misconception. Life jackets do not make us lighter. They have their own mass, their own weight. They're going to make us heavier. But what a life jacket does do is it has a lot of volume without a lot of mass. So when you add a little bit of mass and a lot of volume, that drives down the density of the person plus the life jacket together. Life jackets are either full of foam, which is a very light and very bulky material, or life jackets, sometimes you blow them up, you fill them up with air, another thing that has a lot of volume and not very much mass. So the idea is that you plus the life jacket is less dense than you by yourself. And by being less dense, that means less of you needs to be in the water and more of you gets to be up and out of the water. Plus, by wearing the life jacket in the way that it's designed, we make sure that the part of you that sticks out is your head, right? The part that has both your mouth and your nose, where you need to be able to breathe. Don't wear the life jacket on your ankles. It will keep your feet out of the water and you will drown because you're upside down. Fish. Have you ever wondered how fish manage to go to sleep and not sink to the bottom and get eaten by crabs, or float to the surface and get eaten by birds? Fish have a device inside their body called a swim bladder. And the swim bladder functions in a lot of ways like the submarine. It's a container where they can passively either enlarge it or shrink it, and it has a gas inside of it, and so that adjusts the density of the fish. This works because the ocean's density does not change very much. Changes a little. Part of that's due to temperature changes, but not by very much. So if the fish is swimming near the surface and the water there is a little less dense, it can expand its swim bladder to adjust its density to match that of the water. Or if it's swimming deeper, it can shrink its swim bladder so that it's denser and closer to the density of the water, right? Because fish want to be suspended. as we talked a couple slides, they want to be the same density as the water, so they are not rising or sinking, but can just stay at the same depth, particularly when they want to go to sleep. Sharks don't have a swim bladder. Sharks have to keep swimming all the time, even when they're asleep. So if you're there in your life jacket in the ocean and you see a shark swimming toward you, don't worry, he might be asleep. He might swim right past you. Crocodiles. Crocodiles frighten me immensely. I don't plan to visit Africa anytime soon. Crocodiles have a fascinating understanding of buoyancy and an intuitive grasp of being able to use buoyancy. Right? They spend much of their time in the water. They hunt from the water, and they have a problem in that their muscle and their bone and their lungs and everything make them too light, and they float out of the water. Right? There's this idea that a crocodile looks like a floating log. But if a crocodile looks like a floating log, too much of him is floating out of the water, and the thing that he wants to eat sees him and goes away from the river, and he doesn't get to eat it. But what crocodiles have discovered is that if they eat some rocks, right, rocks are very dense, they eat some rocks, that makes them more massive. They sink down in the water a little bit more until only their nostrils and their eyes stick out, and then their snack doesn't see them and comes down to take a drink, and then becomes a zebra snack or a snack for the crocodile. For a number of years, as they killed crocodiles and cut them open, they were confused as to why there were rocks inside. They did not understand this, and at first they thought the crocodiles had poor eyesight, that they were eating rocks thinking they were fish. But in time, with research, they have found that is not the case. The rocks also help them with the digestion of the things that they eat and swallow whole, but they also adjust their buoyancy. So think about it. The unwise crocodiles either eat no rocks or eat too many rocks. Only the smart ones eat the right amount of rocks. And they have found that the bigger the crocodile, the more rocks that are in its stomach, right? As it grows and adds more muscle and more body tissue that's less dense, it has to eat more rocks to keep itself at the right density. So crocodiles been around a long time, and survival of the fittest, the smartest ones keep breeding, and I'm gonna stay away from them. That's my plan. Divers use weight belts to adjust their buoyancy. Divers also, as they dive down, the buoyancy situation becomes very interesting because the pressure causes their lungs to be squeezed into a smaller space. So they have the same mass, but now they have a smaller volume, which alters their density. And so these weight belts allow them to counteract that effect. It's also very dangerous when diving, when surfacing when diving, because then the opposite effect occurs, right? The gas inside your lungs begins to expand because it's under less pressure. And if you do not exhale that gas, it can actually cause your lungs to explode. And the last one is, of course, petroleum products are slightly less dense than water. So when you have a crude oil spill, the oil floats on top of the ocean, and that can cause a number of environmental issues. I've always found it fascinating because if it didn't float, then you'd get oil leaks and you wouldn't know about them because they just sink to the bottom of the ocean. But the oil floats on top of the water because it is less dense. So now we're going to move on to a point that primarily affects gases. Again, this is true of liquids as well, and we can see this effect in rivers and some other situations, but the practical application is for gases. And that's about this idea of flow rate and what happens as the flow rate adjusts. So first of all, flow rate is represented by the letter Q, and it's simply the product of velocity and area. You might think that's pretty simple, right? The water flows into the pipe at 20 liters per minute, and it flows out of the pipe at 20 liters per minute. And that's true. The flow rate has to remain the same, right? The liquid cannot stack up inside the pipe. It has nowhere else to go. But if the pipe is changing in size, 25 liters per minute coming in, 25 liters per minute have to come out. If the pipe is getting smaller, then the only way to get the same flow rate is for the velocity to go up. Or if the pipe is getting larger, then the velocity would go down. But often we're talking about a pipe that gets smaller over time. So what we have found is that the smaller the constriction, the faster the liquid has to flow. So that's just expressed here very simply, mathematically, right? As area 2 is smaller, velocity 2 is going to have to be bigger. And then they discovered something using something called a Venturi meter, where they could measure the pressure of the liquid in each of those pipes. And this is the sideways pressure, right? That's very important to understand. It's not the forward pressure, it's the sideways pressure that's being exerted. And what they found is that in this small pipe where the fluid is flowing the fastest, the sideways pressure is actually very low, very low. And one explanation of that is that so much of the fluid is moving in the direction of primary motion that there's less randomness pushing in the other directions. This idea of pressure has to be understood in the fact that, you know, fluids are made up of billions and trillions of tiny little particles, and those particles are all moving, as we will talk in the next chapter when we address temperature and the effects of temperature. All those particles are moving, and they're all moving randomly all the time, and that's what generates this idea of pressure that is always present. But when you get too many of the particles moving in the same direction, there's fewer of them moving on average in the other directions. And so the faster moving fluid has less sideways pressure. The slower moving fluid has more sideways pressure. And that is going to be a very important principle that we're going to use. So Bernoulli's principle is what tells us that the faster moving fluid has lower pressure. Okay, that's what the Venturi tube just showed us. A great example of this is the water hose, right? So if you get a garden hose and you're watering the plants or whatever, and you see your friend across the yard and you decide you want to spray them, you know, a garden hose in its normal form is not real great at spraying, right? The water just kind of glugs out of the hose. But if you take your thumb and you cover up, say, 95% of the opening on the end of the hose, you can turn your hose into a water gun, right? And this is that whole flow rate situation. What you have just done is you have greatly restricted the area, right? You reduced the area by a factor of 20, which means the velocity had to go up by a factor of 20, and now you have a water gun to spray your buddy with. So as the area goes down, the pressure goes, the speed goes up, and as the speed goes up, the pressure goes down. So how is that helpful for us? How does that benefit us? Well, this is the whole idea behind an airplane. We have a wing that is shaped in this particular way. The bottom of the wing is always flat. If you've ever made a paper airplane, think about the design that you used. Even in paper airplanes, the bottom of the wing is always straight and flat. The top of the wing is sometimes multiple thicknesses of paper, or in the case of a real wing, is curved and shaped like this. What does that mean? Well, the air going across the bottom has a shorter path, so it can move slower. The air going across the top has a longer path, so it has to move faster. The faster moving air will have less pressure. The slower moving air will have more pressure. We'll have more pressure below, less pressure above. That will put a net upward push on our wing. If we do that in the right way, if we do that moving fast enough, which is pretty fast, right? 100 miles an hour or more, we can get enough upward pressure exerting enough upward force on that wing to lift not only the wing, but the plane that's attached to the wing up into the air. That is not the only thing that planes use to fly. They also use this principle that we learned way back again in chapter 5, Newton's third law. The wing is tilted so that as we race through the air at 100 miles an hour, the air strikes that tilted wing, and the tilted wing shoves the air down. And when it shoves the air down, the air shoves the wing up, right? Third law for every action force is a reaction force. So if the wing pushes the air down, the air pushes the wing up. So we get lift from the third law, we get lift from Bernoulli's principle. Those two things together are what allow airplanes, which are heavier than air, right? This is different from a hot air balloon. A hot air balloon becomes so large and displaces so much regular air that it is effectively less dense than air as an entire object. So we call those lighter than air objects, blimps, hot air balloons. But airplanes and helicopters are heavier than air objects that also can fly. A heavier than air object that flies is going to need to use Bernoulli's principle to do it. And it's going to have to be moving fast, or some part of it's going to have to be moving fast, right? An airplane, we call them fixed-winged aircrafts. The aircraft itself has to go through the air fast enough for this effect to occur on its fixed wing. That's why you need a big, long runway to build up the speed to get enough lift to lift off before the end of the runway. A helicopter, which does not have fixed wings, but instead of moving the whole helicopter through the air, we just take the wing, which on a helicopter we call a rotor, and we spin it through the air at a very high speed, and we generate the lift without having to have a big long runway, and then we lift the helicopter off in that way. So here we have a wind tunnel where they've been able to make the air currents visible, and you can see how it is flowing around the wing, how this air flowing underneath has a very straight, short path, and the air flowing over the top of the wing has a longer path to create this difference in pressure. Turns out Formula One cars need wings as well. I talked about how you get to 100 miles an hour and the aircraft can take off. Well, we have race cars that go faster than 100 miles an hour. So how do we keep our race cars from taking off, especially since a race car is, to a degree, shaped a little bit like a wing, right? I mean, if you think about a race car, it's pretty flat on the bottom, and then the top of it is a little bit larger. So you get that same shape of a wing with the air rushing over the race car. So what they actually do is they put on wings on the race car. They call them spoilers, but they are ultimately wings. The only difference is these wings have their straight part on top and their curved part on the bottom. They are upside down wings. Upside down wings to create more pressure on top, less pressure on the bottom to push the Formula One car down onto the road. This also gives them, helps the wheels grip better and give them better traction to get even more acceleration. But primarily it's to keep them from lifting off the ground and losing control. Supposedly at 100 miles an hour, a Formula One race car has a downforce that exceeds its own weight, which means in theory at 100 miles an hour, a Formula One race car could drive on the ceiling. In theory. I've never seen a video of them doing it. I'd love to see one. Again, upside down wings on Formula One race cars. Very different, of course, from stock cars. Stock cars are supposed to use a stock body type, and so they don't have spoilers or fins like that. Again, some other examples of Bernoulli. Birds use Bernoulli when they flap their wings. That causes the air above their wings to move and swirl in ways that lower the pressure. Hurricanes and tornadoes, you get very fast air moving across the roof of a house that lowers the pressure. Many times shingles and whole roofs get carried away because of the pressure difference, because the pressure in the attic is normal, 14.7 pounds per square inch, and 100 mile an hour hurricane wind is blowing across the roof, reducing the pressure significantly. If you've ever had the opportunity to rebuild a roof or to reshingle a roof, there are these little brackets that you're supposed to put between the plywood called hurricane clips. And that's to try to hold the whole roof together better and to keep this from happening. And again, it's part of it is, yes, the wind just pushing on the roof, but more of it is a pressure difference due to the gases moving very fast. And baseball pitches, the curve of the baseball, the rotation of the baseball causes a difference in relative pressure on the two sides of the baseball, and that causes a Bernoulli effect that causes the baseball to shift laterally while moving toward the plate, right? This is what makes curveballs curve, and all of that good stuff makes it very difficult to hit the ball. also what will make your umbrella do what this umbrella did, right? Again, wind blowing over an umbrella, the bottom of the umbrella is relatively flat, but the top of the umbrella is curved. So the wind blows up and over the curve, creating lower pressure, and that causes your umbrella to invert like that in a gust of wind. Most people think, oh, well, the wind just gets underneath the umbrella and pushes it out. Nope, it's really the wind blowing over the top of the umbrella and the pressure difference that causes that to occur. Curveball. We already talked about it. Not sure why I have it on here twice. So that's the end of chapter 13. I'll see you back here for chapter 14 in a little bit.